Hey, now we're going to talk about Newton's law of universal gravitation, which he quite literally discovered sitting under an apple tree. Okay, now, what the universal gravitation law states that all objects attract masses, and they attract all other masses, and they have a force that's directly proportional to their products and inversely proportional to the radius squared. Now, that was first theorized by Newton. Now, Newton really left it as a proportionality. He said force was proportional to m1 m2 over r squared, and he actually proved it with the moon. He proved that the moon was actually falling towards the earth, but it's moving so fast that it misses the earth. So he calculated how much it did. Now, Cavendish came along later and made an equality out of it. He actually solved for the constant big G. Again, that constant will always be given to you. A diagram of what he did is pictured on the left. What he did was he suspended essentially a dumbbell with two big weights on the end of it from a metal wire. The advantage to a metal wire is by how much you bend it, it creates a certain amount of torque, and therefore they could calculate F. He then had mass 1 and mass 2, which were the green and purple balls, and by varying the distance between them, he could change the torque on the wire. So he knew F, he knew M1, he knew M2, and he knew R squared. Then he repeated it thousands of times, and what he found out was the same constant always showed up, 6.67 times 10 to the negative 11th newtons times meter squared divided by kilogram squared. That is a very, very small number. His measurements were incredibly accurate. Now, the inverse square law, the 1 over r squared on the bottom of that, is really, really what's important. And the key thing is it depends upon the distances between the centers, not necessarily the distance between the surface and the object. So be careful about that. And it's useful in several different ways. One of the most common ways I think of is spray paint. If I take a can of spray paint and I hold it 6 inches away from a wall, I'm going to get a certain amount of spray per square inch on the wall. If I move it back to 12 inches, so I double the distance, the spray paint is the same amount of spray paint is now going to cover an area 4 times larger. So each individual area only gets 1/4 as much. If I move it back to 18 inches, which triples the distance, I'm now going to have the same amount of spray paint, but now it's going to be on an area 9 times larger. So therefore each area gets 1/9 of what it got before. It's a little bit of an optical illusion, but those A's are all the same size. Hold your fingers up on the thing and on the screen and you can see that. So in addition to spray paint, electric field strength and electric force also do the same thing. Light intensity does the same thing, and of course gravitational strength does the same thing. So when you double the distance away from the center of the earth, your weight goes to 1/4 of what it was. So let's calculate G. Again, we know what G is. I've given it to you, but let's calculate it. Now, we know that Fg is equal to big G m1 mass of the earth divided by the radius of the earth squared. So when we're standing on the earth, the thing that controls my weight is, yes, my mass, but also the mass of the earth and the radius of the earth. And I've given you the commonly accepted values. We also know that Fg is equal to m times G. So what I'm going to do is factor out me. I'm m1. So when I factor out me, I get that little g is equal to G mass of the earth divided by the radius of the earth squared. I simply canceled out one of the masses. So now let's plug and chug our values. And if I put all of that into a calculator, if you don't believe me, do it yourself. 9.8 meters per second squared. The math gods are happy. Now, here's what it looks like graphically. If I'm right at the surface of the earth, I feel my normal weight. If I go 1 Earth's radius above that, I'm going to feel 1/4 of my weight. 3 Earth's radius, 1/9 of my weight. 4 Earth's radius, 1/16 of my weight. The astronauts are not weightless. Now, a key thing that gets people sometimes is when you get closer. If you cut the radius in half, you have 1/2 squared on the bottom. 1/2 squared is 1/4. 1 over 1 over 4 is 4 times your weight. So if you go to the bottom of a deep mine, you actually weigh more. Now, problem solving. There's two types of problems you're going to encounter with this. Number one, computational. Computational are strictly plug and chug. You just grab the formula, you put in everything, you get an answer. But the one thing they really like are varying the individual components. Now, the key thing with it is you want to leave the variables in as long as possible. And almost always in that, you're not going to have to use g, because g is a constant on any two objects anywhere. So let's look at a computational one. What is the gravitational attraction between two 50,000 kilogram asteroids that are 3,800 meters apart? F is equal to g m1 m2 over r squared. We plug and chug, put our answers in, and I get 1.1 times 10 to the negative 8 newtons. Now, you might need to check that with your calculator. Make sure you can get that out. There's a lot of stuff you have to put in. I don't want you losing points because of a calculator. Now, sample number 2, this is one where we vary in the individual parts. As a meteor goes from 16 Earth's radii to 2 Earth's radii, in other words, it's coming closer to the Earth, the gravitational force between the two becomes what? Now, let's take a look at it. We're going from 16 to 2, so therefore you have 1/8 of the radius. It's going down by a factor of 8. So therefore the force is going to go up. You're getting closer. Closer means more gravity. Now, F is equal to g m1 m2 over r squared. But here's the key thing, is you need to put 1/8 r squared in on the bottom. Now, here's the thing where you want to leave all the variables in, because now I want to factor out the numbers that were not there before. I have 1 over 8 squared on the bottom, which is 1 over 64. So I have 1 divided by 1 over 64 times g m1 m2 over r squared. Well, g m1 m2 over r squared is the weight anywhere, and it's changed by a factor of 64. So it's 64 times the old force. It goes up, but not linearly. Now, which diagram best shows the gravitational forces between a satellite and the Earth? Well, we know the Earth is pulling on the satellite. That's what gravity says. But we also know that the satellite is pulling on the Earth. That's that's Newton's third law. And since they're both pulling on each other with equal forces, that's the winner. Newton's laws don't change just because we have a new equation. Now, a 2 kilogram object falls towards the Earth. What is the magnitude of the gravitational force of the object from the Earth? Fg is equal to question mark. Well, we know that Fg is equal to g m1 m2 over r squared, but in this case m2 is the Earth's mass, r squared is the radius of the Earth squared. So I'm going to factor that out. Well, I know that g m2 over r squared for Earth is 9.8 newtons. Meters per second squared. So then when I multiply that times 2 kilograms, I get 19.6 newtons. Same way you would have done this problem earlier. So it doesn't change just because you have this law. Okay, let's look at this. This is another one where I'm going to vary the numbers. Planet Q has twice the mass and 3 times the radius of the Earth. Something that we could actually determine from the Earth. We could get the size. We know what it's made of. We could get the density. So therefore we can get this from Earth. It's possible. We know G for every other planet in our solar system. Now, if you weigh 800 newtons on Earth, what would you weigh on Q? Well, we know that g m1 m2 over r squared on Earth is 800 newtons. What we're now going to do is go to planet Q. Now, I put in what should be there. G m1 is my mass. That doesn't change. 2m, because the planet has twice the mass. And on the bottom 3r squared. It's important that the 3 is in the parentheses down there. So now we factor out the numbers that were not there before. You have 2 over 9 times g m1 m2 over r squared. Well, the advantage is I already know what those numbers are for Earth. So it's 2/9 times 800 newtons. So therefore 177.8 newtons. I hope this helped. Universal gravitation, again, the inverse square law is a thing that throws people a little bit, and we'll see it again in other topics we cover in here. Have a nice day.